Okay then, so another very useful kind of piece of category theory gadgetry which we might want to get at is a natural number object. And it turns out that each of these kind of categories of functors from C to set has a natural number object. So what is a natural number object? Well, precisely, it is an object n which has an arrow C from n to n, and also a point, which we'll call 0. So in other words, there's an arrow called 0 from the terminal object to n. And this kind of structure has the property that for any kind of similar structure, but with some object A instead of n, so in other words, whenever we have some object capital A in our category, with an arrow U from A to A and an arrow Z from 1 to A, well then there has to exist a unique arrow Q from N to A, which is such that it makes this diagram commute. Okay, so we have Q after 0 equals Z, and U after Q equals Q after C. So how can we think about all this stuff? Well, think about this 0 here as picking out the number 0 in our natural number object. Let's think about the case of the category of sets because it's simpler. Think about C here as the kind of function that sends a number to that number plus 1, so sort of the successor function. It's usually called S, but since I'm using S so much for other things, I thought I'd call it C. Now, think about A as a set, and Z here is picking our kind of initial point, and then U being a function from A to itself. So we have a sort of dynamical system which starts at point Z in A and keeps updating according to this update function U. And now basically Q is going to send, it's going to send number 0 to the starting point of our dynamical system, and it's going to send number 1 to the position after 1 updates, number 2 to the position after 2 updates in the dynamical system, and so on. So basically Q is kind of keeping track of the evolution of this dynamical system, the numbering of the states starting from the initial one, Z. So the idea of a natural number object then is that in general it's this kind of setup with these arrows 0 and C, such that for any kind of case like this where we have an arrow U from A to A and an arrow Z from 1 to A, there exists this unique Q that makes this diagram commute in this manner. So, okay, what does the natural number object look like in the category set to the power of C? Well, you've probably noticed that there's a lot to get through in this video, and so I'm not going to prove the following. Indeed, I haven't proved the following, but I'm basically going to conjecture what kind of form this natural number object has. And I think it's correct because I've seen quite a few things that basically say that in a topos, you can think of the natural number object as kind of being built out of a load of terminal objects kind of co-producted together. That's very roughly speaking the case. But anyway, so what form do I think the natural number object has in set to the power of C? Well, this n here should be a functor from C to set. And I think if we set n of E is equal to the set of natural numbers for every object E in C, and also for every arrow S from E to V in C, let's let n send S to the identity arrow of the set of natural numbers. Okay, so basically this is a sort of functor which sends everything in C constantly to this kind of set of natural numbers. It sends all of the objects in C to this set of natural numbers. It sends all of the arrows in C to the identity arrow, the identity function of the set of natural numbers. Okay, so that's the nature of this functor n from C to set. Now, we also need some other stuff. So we need this arrow, which we're calling 0, from 1 to n. And I propose we define this so that for every object E and C, the eth component of this arrow 0, well, that's going to be a function from 1 of E to n of E. And we already know that 1 of E just has one element that we could call theta. And I would propose that this function, as in the eth component of this arrow 0 here from 1 to n, it sends this only E-type element theta of 1 here, it sends it to 0 in n of E, because n of E is equal to the set of natural numbers, so it holds this number 0 here. Okay, what about this kind of successor function C? Well, I maybe shouldn't call it a function at the moment, because it's really, at the moment, this is an arrow from n to n in set to the power of C. And so how is it defined? Well, for every object E in C, and for every number x in n of E, I propose we set C of, I suppose we have that the eth component of C sends x to x plus 1. Okay, so this is just like a kind of successor function. It's just it has many components, but they all pretty much look the same. Well, okay, so that's sort of defining the basic kind of structure of our natural number object, at least what I'm proposing acts like a natural number object. So we've defined 0 and we've defined this kind of successor arrow C. Now the only other thing we need to know is how can we find this kind of intermediary arrow? Remember I talked about this kind of Q, which allows us to emulate the effect of another sort of something like a dynamical system. Well, we want to be able to do that kind of thing. So let's also suppose that in our category set to the power of C, we have an object A with an arrow U from A to A, and also a point little z of A. When I say a point of A, I mean, of course, an arrow into A from the terminal object, in this case called Z. So the question then is, how do we define this arrow little q from n to A, which is supposed to make this kind of diagram commute? And I would propose that for every object E and C, we define this q such that, well, we ought to have the eth component of q ought to be sending 0 to z of E of theta, where theta is this kind of only E-type element in 1 of E. So where theta is this only kind of E-type element of the terminal object. And also, for every number x in n of E, we ought to have that q of E of x plus 1 equals u of E of q of E of x. And that's going to be an element, and that's going to be an E-type element of A. And so the idea here is basically that we define q of E so that it sends the successor of x to the thing which we get by updating where it's sent x under our kind of update arrow of A. And I think if we set things up like this, we will have this diagram commutes. And so that's basically all the information we need to set up a natural number object. And of course, then one would wish to prove that this really does make a natural number object, in the sense that, you know, all these different things I've defined are, you know, proper functors, proper natural transformations, that we have a uniqueness of Q and commuting diagrams and all of this kind of stuff.